Hello world, my name is Jonathan Tumim, and today I'm going to show you a project that I've been working on. This is a stress test for Bitcoin, specifically for Bitcoin Cash, and the stress test is to show you what kind of transaction throughput is possible with more or less the stock existing Bitcoin code. This test is going to be running on my desktop computer, which has 12 gigs of RAM and a Core i7 4790K CPU. That's a quad-core, 8-thread CPU that runs at 4 gigahertz. So it's medium high-end, and it's about like $250 for the CPU itself. Nothing too exotic. And this test is going to run with 4 nodes running on this one computer. 4 nodes because it has 4 cores on the CPU, so we're using basically 1 core per node. And these nodes are going to be connected in a chain. So node 0 is connected to node 1, which is connected to node 2, which is connected to node 3. So for a transaction to get from node 3 to node 0, it has to first pass through nodes 2 and 1. Nodes 1, 2, and 3 will be generating spam, and node 0 will be generating the blocks. I'm going to go ahead and start the test now. And the test will go through 4 different rounds of spam / block generation. The first step is just generating the UTXOs that are going to be used for the spam generation. That'll be done in a few seconds, and then we'll start generating the spam itself. And the first round is a little bit slower than the later rounds because the wallets aren't quite yet at their steady state. So the algorithm for selecting coins will be a little bit slower. But even so, it's still pretty fast. So we're currently generating on each node at about 1,200 transactions per second. There are 3 nodes generating, so that's 3,600-ish transactions per second total. This will slow down a little bit over time on this first run because of the wallet UTXO pollution issue. Now, this is happening faster than the validation rate, partially because most of the CPU time that we have is being taken up by transaction generation. So we're accumulating a backlog of unverified transactions, and in a second we'll start clearing through that backlog. Down at the bottom, you can see CPU usage for each of the 4 cores and 8 threads, and you can see we're mostly saturating the CPU. On the right side, you can see bandwidth usage. Keep in mind, this bandwidth usage is for all 4 nodes, so the per node bandwidth usage is about 1/4 of that. So now we have the mempool synchronization stage. So right now we're just working through that queue of unvalidated transactions and validating them as quickly as we can. For each node, we have the transaction count in mempool. So node 0 now has 125,000 transactions in it. Node 3 has 164,000 transactions. And we generated 168,000 total, so as soon as it hits that, it flatlines at that point. And we've got 32 megabytes of transactions in each. So that took 39 seconds to synchronize the mempools, and we were running at an average rate of 3,200 transactions per second per node on a single core. We're now generating the block and propagating it, and you can see that we're only using 1 CPU core at a time for this. And it took 0.2 seconds for node 0 to get that block propagated to it, basically no time at all. But every step after that took around 3.5 or 4 seconds. So it's that right there, that I guess it was 4.8 seconds per hop is the relevant block propagation time. Now, since we're running all on localhost, we have effectively infinite bandwidth and 0 latency. So all of that 4.5 second block propagation time is validation time. The way that the code currently works is that the block has to be fully validated before the node can forward it to the next node. And so because we have a chain of nodes, that means the block has to be validated in total 4 times before the last node gets it. This is not necessary and can be changed. The compact blocks specification actually doesn't require the block to be fully validated, just partially validated before propagation. But the compact blocks implementation does not do this yet. I'm hoping to add this to Xthinner, so soon we should see better performance. Looking back, we had 4,500 transactions per second total generation rate for round 2. I mentioned that the first round is slower, so we're now getting to the steady state. And second block has been generated and is being mined. Mempool acceptance rate was about 2,900 transactions per second. So yeah, this gives you an idea for what kind of resource requirements there are for these kinds of transaction throughput. A single CPU can easily handle 3,000 transactions per second without any multi-threading of the mempool acceptance. And even when we were processing all those transactions and forwarding them amongst our nodes, we were only seeing around 6 or 7, maybe 8 megabytes per second of traffic between all 4 nodes. So each node was only using about 2 megabytes per second of traffic. This suggests to me that a typical home user might be able to run a node that could handle thousands of transactions per second without breaking their budget, without buying any exorbitant hardware. Something to keep in mind, though, is that the bottleneck on what we can safely scale our blockchain to is currently not on the end user side. It's actually at the miner side. The block propagation and validation times between miners is critical, because if that number gets too high, it causes a centralization force. It makes miners want to join together into very large pools, and that compromises the security of Bitcoin. So just because we can do this part very quickly doesn't mean that we should immediately increase the block size limit until we can get thousands. It just means that soon, perhaps, we can fix some of those performance issues, and we can scale it up further than that, further than what we currently have. The transactions that I'm generating are all very simple transactions as well. They're all single input, single output transactions. Those are the worst case scenario for a lot of the different of the full node code. For example, block propagation is slower on small transactions, because block propagation requires a certain number of bytes per transaction, regardless of the transaction size. For compact blocks, it's 6 bytes per transaction. So having the single input, single output transactions should actually make some of the stages worse. However, if you had 2 in, 2 outs, then you'd be getting half as many transactions for a 32 megabyte block, and probably also half of the validation time, because you need to be checking 2 inputs. So yeah, another block at 4.7 thousand transactions per second generation, and validation is still kicking along at around 3,000-ish. We'll see in a second. So this code does have some modifications to the Bitcoin ABC source. Most of the modifications are in the transaction generation, just because, like, normally ABC is limited to generating about 3 transactions per second. Most of that's because the algorithm for choosing UTXOs is very accurate and slow. So I rewrote that algorithm to be less accurate and very, very fast. I also put the wallets on a RAM disk, which made a big difference. That got me from about 70 transactions per second up to about 2,000 transactions per second. The main change that I made outside of the generation code is that I made it so that transactions will be announced after 1 second on average instead of after 5 seconds. And that just allows the mempools to sync a little bit faster. That change is very simple. It's literally 1 character, so it can be made to Bitcoin ABC without any problem. And so there you have it, 4 runs that took around, looks like about 8 minutes. So 32 megabytes times 4 is around 120, 130 megabytes of transactions in 8 minutes on a single computer. And a lot of that time was taken up by transaction generation and was not actually being used by transaction validation or block propagation. So hope that has been informative and helpful to you all. If you want to, you can see my code at and it's in the stress test xthinner branch. While this code does have xthinner support, because it's all on localhost, the xthinner doesn't actually do anything yet. But again, once I have the ability for xthinner to only validate the Merkle root before propagation, that should significantly improve these synchronization times right here and the time per hop. Thanks for watching.